Hi, we talk in this video about the upper bounds and lower bounds of a subset of R. In fact, we already saw how in R we can define a relation, an order relation, that will allow us to put all the elements of R, all the real numbers, on the axis. This order was defined as being the relation between two elements. An element is less or equal than the other element. Okay, and this order was total, or we proved that it's total, saying that any two elements that you choose in R, they can be compared with this relation. Any two elements that you choose, any two real numbers, we have for sure one of them is less or equal than the other one. So the order was total. It can be applied to any two elements you choose in R. That's why we'll be able to define an element that is greater than all the elements of a given subset. Let's say, for example, if I take the subset, the interval 0, 5. Of course, any element for all x in 0, 5, so any element you choose between 0 and 5, x is less or equal than, let's say, 7. Why we can do such thing? Because any two elements in R are comparable with this relation. So if you take x in 0, 5 and any other number outside, let's say 7, you can say x is less or equal than 7. You cannot take an element outside 0, 5 or inside whatever and say, yes, this element, I cannot compare it to an element of 0, 5. No, of course you will be able to compare it because the order is total. So this is how we will define upper bounds and lower bounds. We'll say that if you have a set like this one, 0, 5, and then if you have an element in R that is greater or equal than all the elements that are belonging to this subset, which is 0, 5, then this first element is called the upper bound or an upper bound of 0, 5. Of course, if you have an upper bound, you will have other upper bounds. Here, if 7 is an upper bound, then any other element or any other real number greater than 7 is also an upper bound, like 8 or 9 or whatever. And also we'll define the lower bounds. Lower bounds are elements that are less or equal than any other element in the subset. Let's say, for example, -2 is a lower bound, -3 is a lower bound, 0 is a lower bound, 5 from the other side is an upper bound. Okay, so x is between these two numbers, whatever x is inside the set. Okay, so we say in the definition, a real number m is called an upper bound of a subset A if for all x in A, s is less or equal than m. And also a small m is a lower bound if for all x in A, in the subset A, m is less or equal than x. Let me insist on two things here. First, the set is not always an interval. For example, I can take the set of all, let's say, even numbers less or equal than 8. This is a set. I can take, for example, the set of all the numbers that can be written as 1 over n such that n is an integer. This is a set. This set contains the numbers 1 over 1, 1 over 2, 1 over 3, 1 over 4. This is a set. And for the set, I can look for an upper bound and a lower bound. For example, this set, it has a lower bound and an upper bound. All the elements in here are between 0 and 1, right? So 0 is a lower bound and 1 is an upper bound. And also 2, 3, 4 are upper bounds. And also -1, -2, -3, -1.5, -3.24, all these are lower bounds of the set. Okay, so the sets are not should not be always intervals. They can be any subset of R. The second thing I want to point out in here is that here we are saying an upper bound and a lower bound, and not the lower bound and the upper bound, because if you have an upper bound, then you have an infinite number of upper bounds, and if a lower bound exists, then there exists an infinite number of lower bounds. Let me take again the set, the 1 over n belongs to z. I'm taking this example to point out two things. First, we can remark that the 0, this lower bound I gave 0, is an element that is not in the set. It's outside the set. It does not belong to the set. And 1, the upper bound I chose or I pointed out, is an element that is in the set. 1 is given for n equals to 1. Okay, and also the 0, which is the lower bound I chose, is an element outside the set, but also you cannot find any other real number greater than 0 which can be a lower bound. So it's somehow the closest lower bound that you can find to the set. And you can imagine this easily, right? If you take something greater than 0, of course it will not be a lower bound, because you will always be able to find n big enough so that 1 over n would be less than this number that you chose greater than 0. Okay, this is not the case of 1, the upper bound we chose, because 1 is an upper bound that belongs to the set. So any other number greater than 1 is also an upper bound. But of course you cannot find another upper bound less than 1, because otherwise it will not work, because 1 is an element of the set. So any element less than 1 will not be an upper bound, because it has 1 greater than it, and then 1 is an element of the set. Okay, so here we have many cases of lower and upper bounds that we want to investigate. But before, let me only define an upper bounded set. An upper bounded set or subset is a subset having an upper bound. A lower bounded subset is a subset having a lower bound. And a bounded subset is a subset having an upper bound and a lower bound. Now, back to the issue I was discussing. We will call a greatest element and a least element the elements that are in the set but are greater or lower than all the other elements. So if I take again the case I was discussing, the 1 over n, for n belonging to z, then 1 is the greatest element of this set, but 0 is not the least element of this set, because 0 is not an element of the set, but 1, it's an element of the set. So the greatest element of A, being an element of A, I will call it the maximum of A, or max A, and the least element of A is called the minimum of A, or min A. So there's a difference now between the greatest element, least element, and from one side, and from the other side, an upper bound and a lower bound. You agree, because an upper bound, we can have an infinite number of upper bounds as long as there is one upper bound that exists. But greatest element, we have only one greatest element. It's an element of the set that is greater than all the other elements. But in this case, since 0 is a lower bound, but it does not belong to the set, does not belong to A, let me call this set A. So this number 0 is special because it's a lower bound, it's not in the set, you cannot call it minimum, but it's not also as all the other lower bounds, because you cannot find any lower bound greater than 0. How we can specify this case and differentiate this 0 from the 1, which is an element of the set? This is where we introduce the supremum and the infimum. What's the supremum? The supremum is the least upper bound, and the infimum is the greatest lower bound. So we have three things now. We have the upper bound, we have the maximum, and then the supremum. And from the other side, we have the lower bound, the infimum, and the least element. Okay, so the supremum, as I said, is the least upper bound, and the infimum is the greatest lower bound. So 0 in here, it's the greatest lower bound. It's the greatest number that is still a lower bound of A. So 0 is equal to the infimum of A. and from the other side 1 is equal to the supremum of A, because it's the least upper bound. Okay, so this way I differentiated 0 from the other lower bounds, and I gave him a special name, which is the infimum, because this number is special because you cannot find any element greater than 0 which can be a lower bound. So now we have to pay attention to something, is that 1 is a supremum, and also it's the maximum of A, because it's the element of A that is greater than all the other elements. And A, as I said before, has no minimum, because there is no element in A that can be lower than all the other elements, because if you take one element of A, you can always find an element which is less than this one. So you can find a maximum of A which is 1, but you cannot find a minimum of A. But you can find also a supremum of A which is the same maximum 1, and you can find an infimum of A which is the 0. Let me open two parentheses here and to talk about something else, is what happens when you have a partial order. Why we insist on the total order, the fact that the order in R is total, any two elements can be compared. What happens if you have a partial order? If we take the example that I talked about in other videos about the order that I'm trying to do in a class of students, where I want to put the students in order of their age, but I want to put all the boys together and all the girls together, in the sense that I will not be able to compare boys and girls. The order relation I'm trying to implement is an order relation that works only with boys alone or with girls alone. This way, any two elements in the class cannot be compared. You can compare only boys with boys and girls with girls. So if you take one boy and one girl, they are not compatible with this relation. Okay, so then in this case you will never be able to find an upper bound of the set, because you cannot find an element that is greater in the sense that I'm defining, that is greater than the other elements. If it's a boy, you can say that his age is greater than all the other boys, yes, but you cannot compare it with the girls, and same thing if you have a girl. So you will not be able to find an upper bound. You will not be able to find a greatest element. That's why in these cases, when you have partial orders, you will define something that you call the greater element or the lower element, which are elements that are comparable with their groups. So you have the boy who has the greatest age or the boy who has the lowest age. These elements, you will define them in algebra later. We'll not use them in here, because in here we are in R, and in R we have, thanks God, a total order. So let me insist now on something. When you define a supremum and an infimum of a subset, you should know that the supremum that we denote sub A in here and the infimum that we denote inf A do not belong necessarily to the subset A, like the example I already gave about 0, 1. But when they belong, like in the case of the 1 in the example, they will be the maximum or the minimum of A. They will be the same element. Okay, so now I will take an example which is the interval 0, 1. I take this example which is closed at 0 and open at 1, and we want to discuss the infimum and the supremum of this subset. Well, of course you can notice easily that 0 is a lower bound and 1 is an upper bound, and also 0 belongs to the set and it's the greatest lower bound. You cannot find a lower bound greater than 0, because if you move greater than 0, it will be inside the set. Okay, so 0, it's at the same time the infimum of A and the minimum of A. But 1, it's an upper bound, of course. It's the supremum, because you cannot find another upper bound lower than 1, but it does not belong to A. So it's not a maximum, and you cannot find a maximum of A. Any element that you choose in A cannot be a maximum, because you will find always an element greater than this one inside A. Now, to prove this kind of exercises, we will do some approaches later to teach you how you can write these details mathematically in a correct way. But now we arrive to the most important theorem in here, that says that any empty, non-empty, upper bounded subset of R has a supremum in R. So if you take a subset of R, let's take it upper bounded, forget about the lower bound. If it's upper bounded and it's a subset in R, then it has a supremum in R. You might say, well, that's trivial, there's nothing to do in here. But no, this is not true always. If you take, for example, a set in Q, let's take the set of all, I will call them R, rational numbers. Let's take the set of all the rational numbers such that their square is less or equal to 2. This is a set that contains only rational numbers. So if I call this set A is included in Q. There is no doubt, because it contains only rational numbers. And these rational numbers, they have their square less or equal to 2. Now, we can prove that this set does not have an upper bound less than square root of 2. Any number less than square root of 2 is not an upper bound of the set, because you can find a rational number greater than this number whose square is less than 2. And we can prove that since we are in this case, there is no number less than square root of 2 which is an upper bound, we are sure that square root of 2 is an upper bound of the set. Okay, so it's the least upper bound. We can prove this. I'm not showing the proof in here, but we can prove this. So square root of 2 is an upper bound, and it's the least upper bound, so it's the supremum of this set. But the thing is that this supremum, which is square root of 2, is not rational, it's an R. So this is a bounded set, or at least upper bounded set, that has its supremum not in Q but in R, while the set being in Q. Okay, so this is not the case in R. In R, if you take a set or a subset of R which is bounded or upper bounded, then it has its supremum in R. And it's the same case if the set is lower bounded, then it has its infimum in R. So this is the second part of the theorem. So to prove now that an element is a lower bound or an upper bound, that's relatively easy. To prove that it's a supremum, for example, it's more complicated, because you have to prove that there exists no any other upper bound lower than this supremum. If you take, for example, the interval 0, 1, you have to prove that 1 is a supremum, you have to prove that any other element less than 1 is not an upper bound. But now we can find another way to prove that an element is a supremum or an element is an infimum in this characterization of supremum A and infimum A. In fact, to prove that M is a supremum of A being, of course, a non-empty upper bounded subset of R, then it has a supremum in R. So we have the equivalence between supremum of A is equal to M, and for all x in A, as x is less or equal to M, which means that M is an upper bound of A in this first point, and so it remains to prove that M is the least upper bound. And to prove that it's the least upper bound, we can prove this thing in here that says that for all epsilon positive, so whatever epsilon that represents a real number, so for all real number positive that you choose, any real number, and if you take the point M that is already an upper bound and you go back epsilon, then this new number M minus epsilon will not be an upper bound of the set, because you will be able to find an element in A that is between m minus epsilon and m. Let me graph this a little bit. So we are saying, if this is the set, if this is R, and this is the set A from here to here, it's an interval A. If this point here is a point M that is an upper bound, but I want to prove that it's the least upper bound, then if I take a step back that I call m minus epsilon, so a step back of length epsilon, which is a positive number, and I will arrive here at this point, which is m minus epsilon, then of course you will be able to find a point in here A that is an element of the set. Okay, now you can tell me, yes, but this epsilon, how do I choose it? Of course, the interesting thing is to choose epsilon very small, because if the set A, it goes from here to here, let's say, and you choose epsilon very big, greater than the set, it means that your m minus epsilon will be in here, and of course all the elements of the set are greater than m minus epsilon. So this is not interesting. What's interesting is to take epsilon very small, even smaller than what I drew in here, very extremely small. And even if you take epsilon extremely small, you will be always able to find an A that belongs to the set that is in here between m minus epsilon and m. And if this is satisfied, it means that there is no number less than m that can be an upper bound. So m is really the least upper bound, and it's the supremum. So this is what I call the characterization of the upper bound, and we have the same for the lower bound. So if you take the lower bound small m, and then you move to the right side with a step epsilon, you're able to find an element of the set which is between m and m plus epsilon. Okay, I will take this exercise. I will try to prove it using the characterization. I want to prove now that the supremum of 0, 1 is equal to 1, using the characterization of the upper bound. So in the characterization we have to prove two things. First, we need to prove that 1 is an upper bound, which is true, because any x you choose between 0 and 1, x is less or equal than 1. Of course, it's strictly less than 1, but to satisfy the characterization as it is, because it says that it should be at least less or equal than this upper bound, so it's true in here, it's less or equal than 1. Then 1 is an upper bound of the set 0, 1. The second point is to prove that if you choose any epsilon positive number, even if it's very small, you should be able to prove that 1 minus epsilon is not an upper bound of the set. So we let epsilon be a positive number that can be very small, and try to prove that between 1 and 1 minus epsilon we can find an element A of the set. This is the question. So are you able to find an element A which is a real number between 0 and 1 strictly, that is in the set, that is, between 1 minus epsilon and 1? The answer is yes. If you take A as being 1 minus epsilon over 2, for example, this is a number that it's in here. It's the midpoint between 1 and 1 minus epsilon. So first, 1 minus epsilon over 2, of course, it's less than 1, then, and it's positive, of course, then A belongs to 0, 1. This is the first thing. And then A is between 1 minus epsilon and 1. And of course it can be equal to 1. Okay, so then 1 minus epsilon is not an upper bound of the set. And since it is true for any epsilon you choose, so any epsilon you choose, the proof remains true. You didn't put any condition on epsilon. So this is true even if epsilon is very small, which means that you will not be able to find any number less than 1 which is an upper bound. Then 1 is equal to the supremum, it's the least upper bound of the set 0.001. Okay, I will let you do the same for the lower bound and the infimum. Now, to finish this section, I will recall the theorem, which is the Archimedean theorem, that will be used in our proofs later. The set R of the real numbers is a set that we call Archimedean, which means that for any epsilon you take positive, any number you choose, and any other number you choose x, you will always be able to find p, an integer belonging to n, such that p epsilon is greater than x. So p epsilon is that you are multiplying epsilon by an integer. So you are adding epsilon to itself p times. It means that if you take epsilon very small, even if it's 0.001, let's say, and x very big, 100,000, okay, you are able to add 0.01 as many times as you want, in a way that at some point of time you will be able to bypass 100,000. Okay, this property is called the Archimedean property, and I think you understood the meaning. So you are able to multiply 0.01 by an integer large enough so the results will be greater than x. So this property you will see later where it will be used to in our proofs.